For nearly a decade, one idea has quietly held deep learning together: the residual connection. Since ResNet in 2015, almost every serious architecture, every transformer, every large language model has carried the same humble skip connection: output equals input plus a transformation. It is the reason we can train networks hundreds of layers deep without the signal vanishing. But what if that single highway lane is now the bottleneck holding back trillion-parameter models? In this video, we unpack MHC, Manifold-Constrained Hyper-Connections, a December 2025 framework from DeepSeek that reinvents the residual stream itself and treats how layers connect as a brand new axis of scaling, sitting beside depth and width. To see why the residual matters, start with a plain stack of layers, order 0, where each layer simply transforms the last. Information theory is unkind here. The data processing inequality guarantees that mutual information between the input and the hidden state can only decay as we go deeper. Signal erodes layer by layer. The residual connection, order 1, fixes this by adding the input back. A equals H plus F of H. That little plus sign preserves an identity path, a clean channel through which both the forward signal and the backward gradient flow untouched. This identity mapping property is the load-bearing wall of modern deep learning. Remember it, because breaking it is exactly where trouble begins. Hyperconnections, introduced shortly before MHC, asked a bold question: why settle for one residual lane? Instead of a single stream, they widened the residual into several parallel streams and replaced the fixed plus sign with learned mixing matrices. Each layer can now read from and write to any combination of these streams. Formally, the update becomes order n. The hidden state aggregates the transformation together with not just the previous layer, but several preceding ones. The network stops being a simple chain and becomes a directed acyclic graph of information flow, a multi-lane highway where features can take express routes or merge across depth. On paper, this is strictly more expressive than a single residual. And the expressiveness paid off. Hyperconnections delivered real, measurable gains across language modeling and reasoning benchmarks. By letting the model learn which layers should talk to which, it could route information more flexibly than a rigid residual ever allowed. Researchers saw lower loss and stronger downstream scores, and connectivity looked like free performance. But there was a catch hiding in the mathematics, one that only revealed itself at scale and at depth. The very thing that made hyperconnections powerful, those freely learned mixing matrices, also quietly dismantled the identity mapping property we just called load-bearing. To understand the danger, we have to multiply some matrices together. Here is the crux. In a plain residual, the path from layer to layer is the identity. Multiply by 1, nothing changes. In hyperconnections, that path is now a learned matrix, call it HRes, and matrices compose. The signal arriving at layer 60 has been multiplied by HRes at layer 1 times HRes at layer 2 all the way down. 60 matrix multiplications stacked back to back. If each matrix is even slightly larger than the identity, those small excesses do not add, they multiply. The clean, transparent identity channel becomes a long product of unconstrained operators, and a product of operators is a recipe for either explosion or collapse. Let us put numbers on it. Suppose each mixing matrix has a spectral norm, its maximum stretch factor, of just 1.05, harmless in isolation. But 1.05 raised to the 60th power is about 18. The signal is amplified 18-fold simply by passing through. In real hyperconnection training, the measured composite gain reached 10 to the 3, 10 to the 5, and in toy simulations as high as 10 to the 16, even 10 to the 28. This is exponential amplification in the depth of the network. The identity path, once a quiet wire carrying signal faithfully, has become an amplifier screaming with feedback. What does runaway amplification do to training? It explodes gradients. During backpropagation, that same compounded product multiplies the gradient, so the updates swing wildly, the loss spikes, and training destabilizes, sometimes catastrophically diverging. Practitioners patch around it with smaller learning rates, aggressive clipping, and careful warm-ups, but these are band-aids on a structural wound. Worse, the instability gets harder to control as models get deeper and wider, exactly the regime we care about. So hyperconnections gave with one hand and took with the other, more expressive connectivity, but fragile, poorly scaling training. The architecture needed a principled constraint, not another hyperparameter. The instability has three faces. First, accumulated variance. Summing n residual terms each with unit variance gives variance n, pushing activations toward saturation and gradients toward explosion. Second, mode collapse. With unconstrained freedom, the model finds lazy solutions, ignoring transformations or duplicating the same signal across lanes, wasting the very capacity we paid for. Third, trajectory deviation. Think of the hidden state as a point moving along a smooth manifold. Each layer adds a velocity vector. When those vectors are unconstrained, they yank the feature off manifold, destroying the smooth identity trajectory that made residuals well-behaved. Three symptoms, one root cause. The connection weights are allowed to live anywhere. MHC's insight is elegant and almost obvious in hindsight. Do not let the mixing matrices live anywhere. Constrain them to a manifold, a curved, well-behaved subspace, where the identity mapping property is automatically restored. Keep all of hyperconnections expressive, multi-lane routing, but force every mixing matrix into a region of matrix space that simply cannot amplify or collapse signal, no matter how many you multiply together. That is the whole thesis in one sentence. The question becomes, which manifold has that magical property? The answer comes from a beautiful corner of mathematics, the space of doubly stochastic matrices. A doubly stochastic matrix is one where every entry is non-negative, every row sums to exactly 1, and every column also sums to exactly 1. Rows summing to 1 means each output is a weighted average, a convex combination of inputs. It can mix, but it cannot inflate. Columns summing to 1 means no input is overused or dropped. Mass is conserved in both directions. Intuitively, a doubly stochastic matrix only ever redistributes signal. It is a perfect traffic controller. It can reroute information between lanes, but the total amount of signal entering equals the total leaving. Nothing is created, nothing destroyed. Why does this fix the explosion? Two properties. First, a doubly stochastic matrix has spectral norm at most 1. It cannot stretch a signal, so no single layer amplifies. Second, and crucially, doubly stochastic matrices are closed under multiplication. The product of two of them is again doubly stochastic. So even 60 of them multiplied back to back stays doubly stochastic, with stretch bounded by 1. The exponential blowup we saw, 1.05 to the 60th, is mathematically impossible inside this manifold. The composite gain stays flat around 1. We have restored the identity mapping property, not by removing the learned matrices, but by confining them to a space where compounding is harmless. This space has a name and a shape, the Birkhoff polytope. By the Birkhoff-von Neumann theorem, every doubly stochastic matrix is a convex combination of permutation matrices, and permutation matrices are the vertices of this polytope. That is a deep idea. Permutations are the purest form of routing. They shuffle information from one lane to another without changing a single magnitude. The Birkhoff polytope is the convex hull of all such shuffles. So when MHC confines a mixing matrix here, it is literally choosing a soft blend of permutations, a learnable, differentiable way to say which lanes route to which, while guaranteeing signal is only ever rearranged, never amplified. But there is a practical problem. Gradient descent produces arbitrary matrices, not doubly stochastic ones. How do we project onto the Birkhoff polytope in a way that's differentiable and fast? The answer is a gem from 1967, the Sinkhorn-Knopp algorithm. Take your raw weight matrix, exponentiate every entry so it's positive, then simply alternate. Divide each row by its sum, then divide each column by its sum and repeat. That's it. This alternating normalization provably converges to a doubly stochastic matrix, and because every step is just division, the whole procedure is smooth and fully differentiable. Gradients flow right through it during training. Sinkhorn-Knopp is not just a normalization trick. It is the workhorse of modern optimal transport. It solves an entropically regularized transport problem, finding the lowest effort way to move probability mass from one distribution to another. That framing is what makes its iterations behave like a denoiser. They find the minimum effort, smoothest routing across lanes, filtering out high-frequency noise, and it converges astonishingly fast. About 20 iterations drive the row and column, sums to within 10 to the minus 13 of 1. 20 cheap matrix passes by us a guaranteed doubly stochastic projection, a tiny price for unconditional stability. Here is the most beautiful experiment in the paper, what we'll call the Manifold Dial. Plot composite gain against the number of Sinkhorn iterations, k, at k equals 0, no projection, pure hyperconnections. The gain explodes exponentially with depth, just as we predicted. But watch what happens as we turn the dial. By k equals 1, the gain has already collapsed toward 1. By 5 to 10 iterations, stability is essentially locked in. And by 20, the composite gain stays bounded around 1.6, even at depth 64. The transition from chaos to stability is almost instantaneous, a single dial smoothly interpolating between unconstrained hyperconnections and a fully manifold-constrained ResNet stable network. Now the full MHC connection. Instead of a passive plus, the residual becomes a learnable operator with 4 parts. H-pre, an input filter, projects the streams into the layer, gated by a sigmoid so it stays in 0 to 1. F is the innovation, the actual transformation, attention or MLP. H postgates how much of that innovation is written back, scaled by 2 sigmoids so it can amplify when needed. And H-res, the critical piece, is the residual mixing matrix, passed through Sinkhorn-Knopp so it lives on the doubly stochastic manifold. 3 learnable gates plus 1 manifold-constrained router. Expressive like hyperconnections, stable like a residual. Step back and appreciate the design. Hyperconnections broke the identity mapping to gain expressiveness. MHC asks, can we keep the expressiveness and get the identity back? By constraining only H-res to the manifold, while leaving the gates free to learn, it does exactly that. The forward signal is rerouted but never amplified. The backward gradient flows through a product of doubly stochastic matrices that can neither explode nor vanish. The model keeps its multi-lane freedom to decide what connects to what, but every one of those choices is now a soft permutation. Expressiveness and stability stop being a trade-off. None of this matters if it's too slow to train. 20 Sinkhorn iterations per layer, on every forward and backward pass, sounds expensive. DeepSeek's answer is heavy infrastructure engineering, custom QDUTA kernels written in Tellang, kernel fusion to avoid memory round trips, selective recomputation to save activation memory, and overlapping the extra communication with their dual-pipe scheduler. The result, on a 27 billion parameter model, MHC adds only 6.7% training overhead over a standard residual, a fundamentally richer connectivity scheme, restored stability, for under 7% more compute. That is what makes MHC practical rather than merely elegant. And the payoff on real benchmarks. Across reasoning-heavy tasks the ordering is consistent, baseline residual, then hyperconnections, then MHC on top. On BiG bench hard, scores climb from 43.8 to 48.9 to 51.0. Similar gains show up on GROP, GSM8K math reasoning, and MMLU. Critically, MHC eliminates the loss spikes that plagued hyperconnections. During training, the curves are smooth. And the gap over the baseline widens as models grow from 3 billion to 9 to 27 billion parameters. The method does not just work, it scales better than what it replaces. This leads to the paper's boldest claim. For years we scaled models along 2 axes, depth, more layers, and width, bigger layers. MHC proposes connectivity as a genuine third axis. How richly and how stably layers are wired together. Because the gains widen with scale rather than saturating, connectivity behaves like a real scaling dimension, not a one-off trick. It reframes architecture design from brute force. Just add parameters to intelligent routing. Spend capacity on how information moves, not only on how much you have. Optimal transport, baked directly into the backbone of the network, becomes a lever for scaling. MHC is powerful, but not free of open questions. The identity is now soft and distributed across lanes, which may demand careful reassembly. Its additive memory makes forgetting stale information hard, a write-only memory problem. It's sensitive to initialization, and the 6.7% overhead relies on specialized kernels most labs don't have. Still, the core lesson is durable. By projecting the residual stream onto the doubly stochastic manifold, using Sinkhorn-Knopp and the geometry of the Birkhoff polytope, MHC restores the identity mapping that made deep learning work, while unlocking the expressive, multi-lane connectivity that pushes it forward. Stability and expressiveness finally on the same side. That's MHC.